So first, as usual, do you have any question before we start lab 8? Any question, any comment, any concern?
Doctor, I have a small question for the lab report about the inertia. In question 5, where we have to find the theoretical value of the inertia, you told me via email to use the theoretical formula in the PowerPoint. I searched, and the only formula that seemed a bit logical to me was the one that was I equals mr squared for the ring and disk together. But I used this formula and the number was huge and the percent error was more than 100%. So which theoretical formula should we use?
All right, so if I'm not mistaken, I was expecting you to use this one for the ring and this one for the disk. And ring and disk together, you simply add them. Be careful which mass you're using. It's the mass of the actual disk, the mass of the actual ring, and not the hanging mass.
Oh, okay, thank you. So we just add them up. There isn't any formula specific for the ring and disk together.
No. I is the moment of inertia is very similar to mass. It's a scalar, and usually we add I. Do you remember when we did that? And we have the moment of inertia for each item, for each particle, you simply add them up. And when you want to do the whole rod, you take small items and you do the integral. The integral is adding up in another way, you know? Yes.
Okay, thank you so much, Doctor.
Yeah, and experimentally, we were supposed to find I using this equation, but M inside the experimental I, the equation for I, is the hanging mass. Be careful, because a lot of students were emailing me and they were confused between the different M's. Yeah. Sometimes when you have confusion, you don't really enjoy the lab and you miss the point of it. And I'm sorry for that. So be careful with those tiny masses. Yes, Zilla. Any other question? Shall we start with lab 8? Lab 8 is really nice. It's really nice. All right, so I'm gonna take your silence to be positive. So standing waves in an air column. I'm gonna assume you did not do it in the course yet, and all you know about standing waves is some bits and pieces. You could know from grade 11 or not, because a lot of schools cannot offer standing waves, or probably they do. And some bits of pieces you know from grade 12, I don't know, depending on your program. So do you know anything about standing waves? Hello, Mia. Yes? Do you know anything about standing waves? Did you start in the course? Tell me a bit about it. All right. She's very ill. I'm so sorry to hear that. Yes, no problem. We're recording the session for Yara. So, yeah, I hope she recovers very quickly. So, yeah, concerning standing waves, can you tell me a bit about what you know? Or did you cover that in the course? Can you tell me about that? Do you remember anything from high school, or is it negative for both questions? Nothing from high school and nothing from the course. Is that it? I'm asking you a question. I'm waiting for an answer. All right. So, okay. And all this you remember from high school, nothing from, oh, we didn't do anything in high school and didn't start. All right. So let's assume this is a completely new topic. Okay, this is the outline I'm gonna follow. What are standing waves? And probably take some time for item 1, and you're gonna see it's not something difficult. Probably it's new, like you need to understand, but eventually the math and the physics behind it is so easy. We're gonna start by standing waves on a wire. I know that we're working with standing waves in a tube. It's a sound wave, longitudinal, and an air column. It's a tube, empty tube. But we need to understand how standing waves actually behave in a wire before we discuss what happens in a tube. And then I need to discuss the displacement nodes. Obviously, you don't know what nodes are, and pressure nodes. And I need to explain the experimental setup. And eventually, the setup means what are the equipment and how probably the connection is going to be happening. And eventually, what to do, like the steps, the procedure, and the measurements. Okay. The lab is not very difficult. Probably you have, data analysis is not time consuming. Probably you have one plot, but your understanding of the concept is very important. Otherwise, you're gonna be confused between the different items. It's exactly like inertia, rotational inertia. Confusion was happening because some of you did not understand the whole concept very well. What are standing waves? Clara said the amplitude remains in place. So this is the only thing you remember. So and let me take it from here. Can I? Yeah, I can. Copy paste, the amplitude remains the same. Anyone remembers? Ya Allah, the text box, I don't like it. The amplitude remains in place. What do you mean, Clara? Can you elaborate a bit? Yes, the amplitude.
It means يعني the wave doesn't move as in إنه يعني مثل كأنها بتطلع وبتنزل بس مش إنها عم تتحرك.
Exactly. So the wave does not travel forward. It is standing like it is a local wave, something like that. A local wave. I don't know, probably. Yes. Do you know the reason why? Okay, fine.
She constant.
Something is constant, we don't remember why, and it's okay. Let me start by discussing a bit what is a wave and what is a wavelength. I know this, you know this, but I'm gonna use it. So this is a wave. By the way, a wave is not a vibration. The difference between vibration and wave, the vibration is local, like the vibration of my vocal cords at the moment. You can try to touch your own vocal cords and create a sound. You're muted, you can do that. So the wave, however, the wave is a bit different because it travels forward. So it has a velocity of propagation, direction of motion, it has distance covered, time taken. The wavelength is the length covered between or during a period of time that is exactly one period. All right. So if you measure the length between a peak and a peak, I'm talking about any water wave done in any container or on the beach, So if you check the peak and another peak, and the length between two peaks would give you the length of one wave, okay? You can also measure the wave between a trough and a trough, or measure the wave between a zero, or whatever you want to call it, and another zero. If you want to measure the time taken to cover this distance, you can call it a period. Okay, so now if I need to discuss the speed v, the speed is distance over time usually, like total distance over total time. If I need to take only one cycle, the distance is gonna be called wavelength, and the wavelength, I'm gonna use the Greek letter lambda, and the time will be called period, and the period again is the time for only one cycle. You know that 1 over period is frequency, right? Or the frequency by definition is how many peaks you have per second. You will end up with lambda times frequency. And this is the equation you already have here. Frequency is 1 over second or hertz. So I can probably add what just happened, add some units. So this is in hertz. What is the unit for speed? Help. Yes. SI unit for speed is meter per second. And for the wavelength, SI unit for wavelength is length, wavelength, meters, exactly. So, and it's actually obvious, isn't it? If you look in here, you have meter per second for this guy, and meter and 1 over second. 1 over second is exactly hertz. All right, so this is a wave traveling. So this is very general. This has nothing to do with the standing wave yet. So now, and the next slide is, what I'm trying to explain is the following. You have an incident wave. So this is an incident wave. It's going to the right. Okay. And this is another wave coming from the right to the left. This could be incident and this could be reflected. I'm going to discuss the reflection later. And the two waves are going to superpose or interfere together. Okay. Probably I should talk about reflection now, and this is the reflection I'm talking about. This is a pulse. So the pulse is not a wave because it's only one peak. It's traveling in this direction. It's gonna hit a fixed end, and eventually you will have a reflection in the opposite direction. You see the reflection happening in the opposite direction. So this is a reflected pulse. If I keep on adding pulses non-stop, and then the pulse is gonna be called a wave, and I will have an incident wave and then a reflected wave. The incident wave is not gonna stop, the reflected wave is not gonna stop, and eventually they're gonna superpose and create some chaos. Sometimes, under certain conditions, the chaos is gonna look so pretty and it's gonna look like a standing wave. A standing wave means I will have this pattern, I'm gonna call it a pattern. This pattern is oscillating up and down so quickly. It's a pattern due to the superposition of an incident and a reflected wave. Those points are not moving at all, so you can simply like touch the wire in this region and you see it's not gonna affect your standing wave. You can clip it as well, add something on it, and this something is not gonna fly off. And this will be a region where you have a lot of displacement. Okay, and you can try this at home with a shoelace. I know you need to rotate a bit. You can do a lot of oscillation. Somebody can take the shoelace from the other side with a fixed end without any motion. You can create one loop. You can also have a greater oscillation, like faster frequency, higher frequency. You can create two loops. Probably I can try it with someone and show you, because sometimes when you study standing waves, you think you can only do this in the lab. However, when you realize you can do it at home, it makes more sense to you. So far, what are standing waves? We have an incident wave and a reflected wave. They actually meet and the wave is not gonna stop. So the incident wave is continuous, the reflected wave is continuous. When they meet under certain conditions only, you will see a resultant. So this is a resultant of both happening at the same time. It's not wave one, it's not wave two, it's the resultant. It looks like this, okay? Now those are the different, so this is a wire, this is you, Clara, and this is Mia holding the other side of the wire. So yeah, I'm talking about a wire or a shoelace. So let's say Clara is creating the motion and Mia is not moving because she is the fixed end, and this is the fixed end I'm talking about. You can move the vibration at a certain frequency. You can create one loop. Higher frequency, you can create two loops, and two loops means this one is gonna go down while this one is gonna go up. So quickly, you will not see the actual motion and slow-mo. You will see a loop, but a loop is actually some motion happening. However, yes, you did that in school, I know, and it's okay if you forgot. So this is a node because here no motion is happening at all. You can, so Clara was here. Clara can create a vibration with higher frequency. She can create 3 loops. I will try to show you 3 loops. Probably this afternoon, I'm gonna try the video. 4 loops is so difficult on my hand because my shoulder is gonna collapse with very high frequency. I cannot do it. I tried. It depends on how tense, like the tension in the wire as well. We will see about that. So now what you need to know is the following. This is a complete wave. In other words, this has the same length as the wavelength. So this is similar in length to lambda. Now my question for you is, how long is one loop? If this is lambda, how long is one loop? How long is this loop? How long is this loop? How long is this loop? Tab, how long is this loop? Can you guess? Wrong guesses are also allowed. All right. So Mia is saying that this length is 1/3 of who? Probably she meant of the length of the wire. Yes, so the whole length is called L, the length of the wire, which is a constant. However, if I try to check how many wavelengths, each loop is lambda/2. Since this is how a wave looks like, This is a complete wavelength. If I do the following, the whole thing, I'm sorry for this ugly wave, this one is wavelength, and this one is wavelength over 2. So now you know that the whole thing is L. This is wavelength over 2. Here you have 2 wavelengths over 2. Here you have 1, 2, 3 wavelength over 2. And this is 1, 2, 3, 4 wavelength over 2. So now the length of your wire can be, or can, what's the word for it? It can make space. This is not the word I was looking for, but it's similar. It can make space to half a wavelength. The length here would make space to 2 half a wavelength, which is a wavelength. And this will make space for 3 half a wavelength. And this is 4 half a wavelength. So how come, what's the difference between the different cases? How come the length is sometimes half a wavelength and sometimes 2 wavelengths and sometimes 3 over 2 wavelengths? What was the variable? That's the question. What did I vary to get case 1, 2, 3, and 4? If I need to do the same number of waves, how can I do that? The frequency, yes, Mia. So basically, Clara was creating a vibration. N equals 1 is the first harmonic. She did a regular frequency. N equals 2, second harmonic, it was double the frequency. N equals 3, third harmonic, it's triple the frequency. And you know, as the frequency increases, I'm so sorry, did I lose anything? No. When the frequency increases, the wavelength is gonna decrease, and that's why one big L will fit more and more loops, because the loops are getting smaller and smaller. That's it, you know. Why do I have a smaller wavelength? Because the frequency is increasing and increasing. So now you know that one wavelength in this case is 2L. So you know L is half a wavelength, which means a wavelength is 2L, and then a wavelength is 2 over 2L, a wavelength is 2 over 3L, a wavelength is 2 over 4L, and you can do a general equation which gives you that if I have n loops, I would have n lambda over 2. So I'm going to write it down. N lambda over 2 will fit in 1L, which would give me that L or 2L times 2 is equal to lambda. Am I right? 2L divided by N is equal to lambda. So this. Now my question for you is the following. I need people to help me with the frequency. How do I calculate the frequency? Do you want to try? How do you calculate the frequency? Going back to the equation of frequency. How do you calculate the frequency? We do V over lambda, right? So let us try it here. So I'm gonna say V over lambda. And I already know that lambda is 2L over N, right? So it's gonna be V over 2L, right? Times N, what's that? L times N. Okay, so for the first harmonic, I'm gonna get V over 2L. For the second harmonic, I'm gonna get 2V over 2L. For the third harmonic, I'm gonna get 3V over 2L. And you see that all the harmonics are the multiple of the first harmonic, right? So if you start with a frequency of 100 Hertz, the next one is gonna be 200 and then 300, because you see it's proportional to N. And by the way, N is the integer, it's the number of loops. You cannot have half a loop. It's one loop or 2 or 3. It's an integer, you know, and it's a positive integer. What else I need to tell you? I would love to discuss a bit the speed. Can I vary the speed of the wave in a wire? Any idea? I'm assuming the speed is constant. What can I do to vary the speed? Is it possible actually? The speed of the wave. So I can vary the frequency of the wave by increasing the frequency of the vibration. How about the speed? I can create a vibration, but can I push the wave faster? What do you think? Anything that would help me vary the speed of the wave? Any idea? Anything? Wrong answers are welcome. All right, so no answers. The speed cannot be controlled. The speed depends on the medium only, and I would love to talk about to type it down. So the speed depends on the medium only. In my case, what is the medium in this case? Yes, anyone? Where is the wave traveling? What is the medium I'm talking about? It is the wire. So the best way to change the speed of the wave, I can have a thicker wire. So the mass of the wire is very important, how heavy it is. And what I can do, I can increase the tension in the wire. Like if the wire is really tense, like if you pull it from both sides, it's not loose, it can create a higher speed. Otherwise, there's nothing on earth that would change the speed of the wave, only that, okay? And this is very important. Now I'm gonna move to the pipe or the tube or anything you wanna call it, like the air column. I need to discuss a bit reflection again. And what's the difference when I have a fixed end and an open end? Here I have a fixed end because the wire is attached to Mia's hand and Mia's hand is not moving at all. It could be attached to a pole or anything like a rod, okay? So due to the Newton's third law, for every action there's an equal and opposite reaction. You see that the wire or the cord is pulling on the pole or the rod, and the rod is gonna pull in opposite direction. So that's why you have an incident and a reflected pulse, but the reflected pulse is opposite. So when the incident wave is up, the reflected wave or pulse is downward. This is very important because when those two will add up, they're gonna cancel somehow because you have positive and negative. So every time you have a fixed end, I'm talking about regular reflection of a pulse or a wave, it has the reflection is opposite to the incident pulse or wave. However, when you have a free end or an open end, and you can try it with a shoelace, you stand on a very high table and you do a pulse or a wave and nobody is holding the wire from the other side, you will see reflection. The wave is going to reflect up, but it's going to reflect as if you have a free end. It's not super visible within shoelace, but you will see it very lightly, slightly. And sometimes I try it in the classroom. So how can I create a free end? I can create a ring that is loose and free to move up and down on the pole or the rod, and you will see that the incident pulse is upward and the reflected pulse is going to be upward as well, due to the fact that the end is not fixed to the pole. All right, now I'm going to create a tube, like an empty tube, and instead of doing waves on a wire, I'm going to create sound inside the tube. Okay, sound inside the tube. I'm going to discuss the sound in a bit, but the loops are going to be a bit different. When you have an open end, you can have an open loop. So this is the open end. So you have an open loop and then a closed loop here because you have a closed end. So this is a tube that has one of the ends that is closed and one of the ends that is open. By the way, the same thing happens if you have a wire, but one of the ends is open and one of the ends is closed. In other words here, if I take L and I need to ask you guys, how long is this? If I consider this to be half a loop, how many lambdas is this? Let's assume no answer. Can you remind me how many lambda is one loop? So one loop is half a lambda. This is what Mia and George probably are saying. So half a loop is how many lambdas? Half a loop is how many lambdas? It's a quarter of a lambda. Okay, so let's do the calculation together. In this case, the length of whatever empty tube you have, I'm gonna call the whole tube L. The length is gonna be lambda over 4. In this case, how many lambda over 4 do you have? How many lambda over 4? 3 lambda over 4. And in this case, how many lambda over 4? 5 lambda over 4. What if I have the n case? How can I write this in general? Can I say L is equal to n lambda over 4? Okay, I'm gonna accept it, but what's n? Is it any integer? 1, 3, 5, right? Can it be any, only the odd ones? So I'm gonna write 1, 3, comma 5, and so on. In the course, you can write it, to write an odd, you can write 2n plus 1, because 2, or you can call it 2k plus 1, where k is the integer. 2k is always even, 2k plus 1 is always odd. So in the book, in your textbook, you're gonna see 2k plus 1, lambda over 4. Okay, if you want, we can call it simply n for simplification, but keep in mind n is not an integer, it's only the odd integers. Okay, all right, what else? I need to ask you here the following question. What is the variable here? How come I have a half a loop and then 1.5 and then 2.5 loops? Something has changed. What is it? It has to be something, a variable. The distance between the ends, right? What do you call the distance between the ends? Wavelength, speed, frequency, what? Let's give it a letter. Is it the wavelength? Is the wavelength a variable here? People, just unmute yourself. You're barely 5 students. You sound so shy. I know you're not shy, but this is how you sound. So what is the variable? Zilla said it right. Just tell me, is it the wavelength or the frequency or the speed or what? Somebody should know. Why no, George? Am I disconnected, by the way? What just happened? ايه وين الصبيان؟ ما في بس جورج. All the pressure is on you. I thought I got okay. Yes, that's true. So when we were playing with the shoelace, like the wire, we were increasing the frequency. And you see that the loop is getting smaller and smaller, and I can fit more loops inside L. However, in this case, I don't see the wavelength getting smaller. Something is changing. And Zilla said it so well. She said the distance between the ends. So the distance between the ends, isn't it L? So when n increases, it's basically the fact that L is increasing and not the wavelength that is decreasing. So the difference between these is actually the fact that the length of the tube is getting shorter and shorter. And this is what we're gonna do in the experiment. We have a piston and we're gonna, so this is where the piston is gonna be, and we're gonna close the tube and make it shorter and shorter and shorter and observe what happens to the wavelength, or probably count how many loops and so on, okay? Anyway, so far what you need to know how the loops are, and what is first the reason we have standing waves. Two, how the loops are displaced on a wire when I have two fixed ends, and then how the loops are displaced in a tube. Sorry, when I have a closed end and an open end. Now, one question before I move on. What's the difference between a wave on a wire and sound wave in a tube? There is one difference, a minimum of one difference. Sound in a tube and wave on a wire. And I'm gonna type it here. The sound in a tube, because it's gonna change a bit the way we see things, and the sound wave, let me call it sound wave in a tube, and the wave on a wire. What's the difference? Wave on a wire. There's a tiny difference that is so important. V, because the change in the medium. Oh, definitely. The tube, you have air inside, so the speed is different. And on a wire, we're talking, the amplitude can differ. That's true. The amplitude can be anything. I can have high amplitude vibration, and the sound in the tube, I can scream inside the tube. So they're not even related. V is interesting to discuss because we have two different media. But what's the difference between a sound wave and a regular wave on a wire. The wave itself, what's the difference between the two waves? It's a different type of wave. What do you call, what, it has a name. The type of the wave. You have no clue? We have two types of waves only. Some are something and some are something else. Sound is different than light, water wave, wave on a wire. So those are one class and sound is a different class. What's the difference? You can't, longitudinal, thank you, Clara. So this is transverse. Am I typing? Transverse. And this is longitudinal, yes. And what's the difference? Can you try to explain or probably describe longitudinal? All right, so longitudinal waves are actually waves that where the vibration of the particles of the medium are parallel to the propagation of the wave. So we can talk about compression and rarefaction. On the other hand, when I have a transverse wave, I can talk about a peak and a trough, and the vibration of the particles of the medium are perpendicular to the propagation of the wave. So here you don't actually see a loop going up and down. You will see something else. You will see something like compression and rarefaction, compression and rarefaction, and I'm gonna talk about it in a moment. But it's so much easier to visualize sound to be loops because you can count how many loops you see, but this is not what's happening in reality, okay? Probably I can put this in a box or something so I can keep it, because I want you to see this well. It's very important. All right, now let me start discussing what are displacement nodes and pressure nodes and what's the difference, because in the lab you cannot see displacement nodes. So far I've been talking about displacement and motion and points that are not moving, and I have no means to measure displacement. Okay, reminder, this is a standing wave. I have two fixed ends. This is the easiest example. This is called a node. I'm just giving you the vocab because I know you know what I mean, but probably you don't know the name for it. And probably in French, it's called something else. And this is a node, and this is a node, and the extremities are nodes as well. And whenever you don't have a node, you can say antinode. It's like the middle of the big loop. You can call it antinode. And this is another antinode, antinode, antinode. I'm talking about displacement nodes and antinodes, okay? We are gonna use a microphone. A microphone does not measure displacement. It measures pressure. And as this will vibrate up and down so high, so an antinode means maximum vibration, it's gonna throw the air in both directions. So you're gonna simply think about longitudinal waves. Let me zoom in. And you need to think about maximum vibration, meaning like air is gonna vibrate so high in this region. All the air is gonna be thrown in this direction and in this direction. This region will have a very high pressure. This region will have a very high pressure. And this region will have a very low pressure. So low will be called node, high will be called antinode. So this would be a pressure antinode, and this is a pressure antinode, and this is a pressure node. Node means no pressure at all. Due to the very high vibration, you will have zero pressure whatsoever. So now you can simply say every time I have a displacement node, I can call it dN, I have a pressure antinode. And every time I have a displacement antinode, I will have a pressure node, and so on. So if your microphone would measure very high intensity, it is a node, if you want to draw it. So if you want to count the number of loops, you probably need to locate your nodes or probably your antinodes. So high pressure on the microphone is actually high pressure means a node, yes. All right, for us to have a quick review, displacement is this when I have maximum displacement, and it could be basically the whole loop. I have a zero pressure. When I have zero displacement, I have maximum pressure. zero pressure maximum displacement, and so on. All right, so now you have zero displacement. This is confusing for me, just a second. The pressure is the red one, right? And zero pressure for me is here. Okay, let me check this one. Is this more visible? Pressure. Okay, this makes more sense. Let me remove this. I don't want you to look at it. Probably it's not wrong, but it's confusing. This one makes more sense. I have high pressure, which means a lot of pressure because air particles are close. This is minimum. Okay, now I get it. Minimum is minimum pressure. All right, so this is not basically the loops I'm talking about. I wish I found a different one. Anyway, if C means compression or means rarefaction. C, compression, rarefaction means less pressure, and so on. You can simply keep in mind that every time you have a pressure node, it's a displacement antinode, okay? Yeah. Are you ready for the equipment? What we have? We have a tube. And by the way, this is a piston, like the piston is gonna close the tube. The empty tube is here only. Yeah, so this is where empty is, and the piston is gonna close the tube. What I have here is a speaker. This is a speaker, and the sound is gonna be so, it's gonna bother your partners a lot and your team, your classmates. So usually we ask you to have a very low amplitude, otherwise you're gonna hear nee all the lab session. And the speaker, these are the plugs of the speaker. So you can connect the speaker to your function generator. Okay, this you need a plug, like common plug, and a BNC cable to go into one outlet. And then you can pick anything sound, sinusoidal is what I'm gonna pick. This is the amplitude, you can make it higher or lower. What I care about is the frequency. So we're gonna pick 0.5 kilohertz, 1 kilohertz, and 1.5 kilohertz, okay? Also, I'm gonna use a microphone. There's an empty, like a tiny hole here. I can insert the microphone, and I'm gonna keep the microphone at the beginning of, like at the first end of the tube, okay? I just need to measure a resonance or a standing waves in general. So when it gives me very high amplitude, I'm gonna assume these are loops. I need to show you something, by the way. When you have randomness, the amplitude is low because it's gonna give you something that is practically averaging out to zero. When you have one loop, it's gonna be big amplitude. Even two loops are gonna be bigger amplitude than randomness, because randomness will be chaos that averages out to zero, you see? So when the microphone will measure something high, you can actually hear it, you don't need to see it. Yes, when the microphone, by the way, the microphone is connected to the oscilloscope, and you can see a wave that goes high, then a wave that would go so low. High means I have loops. Low means I have randomness. Okay? So I'm gonna start with very small length, and I'm gonna get randomness. I'm gonna increase the length by moving the piston backwards. The randomness will give me very high amplitude and then nothing again. I will put the piston at the position that would give me very high amplitude, and I'm gonna record the length. I don't know how many loops, but I know I have a certain number of lambda over 4, an odd number lambda over 4. So let me show you a bit the results before I move on. When we stick to a frequency of 500 hertz or 0.5 kilohertz, we had resonance. Resonance means a certain number of lambda over 4, odd number, at those distances, this, and this. Since you have no means of looking at your loops, you cannot see them, they're invisible, you can only tell that the difference between these two is known. Let me ask you, and probably ask Zilla. Zilla, the difference between this length and this length is how many lambdas? Yes.
1.5.
Exactly. No, it's half a lambda. So the difference between, if I do all this minus all this, I get only one loop, which is lambda over 2, right?
Yes.
All right, so this is what we're gonna do. We're gonna take two consecutive lengths and do the difference. So if I take the big one minus the small one, I get lambda over 2. I can write it here. And if I do this one, so this one minus the one just before, I get lambda over 2. Then I find lambda, then I can find the average. Okay, for very small frequency, lambda is gonna be big, and I don't have many lengths because the tube is around 1 meter. But for higher frequency, lambda is smaller and I can fit more loops inside. That's why I have 5 different cases. Probably this is lambda over 4. Probably this is 3 lambda over 4. Probably this is 5 lambda over 4. But just for me to reduce the sources of errors and to be more precise, by doing L2 minus L1, I can find lambda over 2. L3 minus L2, I get lambda over 2. L4 minus L3, lambda over 2. L5 minus L4, lambda over 2 again. Because if I do the calculation, otherwise probably I'm not going to be very accurate. However, it may work as well, okay? So again, back to our tube, I'm gonna take the length and the one that is consecutive and smaller and do the difference between them to take one loop, which is lambda over 2, because I have no means to know how many loops is inside or if it's an open tube or not and so on. But we know for a fact it's an open tube due to the fact that we have a speaker. This is a different picture of the setup. So you see the speaker attached to your function generator. The microphone is not visible. It's tiny. Probably you can see it in the video. By the way, I did not explain that the best way to find the speed of the sound is to follow the theoretical equation. This is the speed of sound in air at 0 temperature, 0 degrees C. By the way, the unit here is degrees C. So we measured the temperature for you, and you can calculate the speed in the tube. So knowing the speed and the frequency, you can find the theoretical wavelength and then calculate the wavelength experimentally and compare later on. I showed you this, so please zoom in to check the smallest subdivision and find the uncertainty whenever it's needed. So I don't know if it's 18 or 18.0 or 18.00. Please check it out for yourself. And then probably they would ask you to find the uncertainty on V. I can't remember. Now, the last part of the experiment is this. They want you to move the microphone. So do you remember the fact that the microphone was at the end of the tube fixed? Now I'm gonna fix the length, like pick a length that I already measured, for example, 3 centimeters or probably 72 centimeters. I know I have standing waves because I already did the measurement. And instead of changing the position of the piston, I'm gonna move the microphone to measure how many maxima, minima, maxima, minima, maxima, minima, nodes, antinodes, nodes, antinodes, and to be able to count how many lambda over 4, 1 lambda over 4 or 2 lambda over 4. Going back to our diagram, if you measure the maxima, this is a maxima, this is a minima, this is a maxima, this is a minima, this is a maxima, right? So how many do you get? Let's say I cannot measure this one because it's like touching the thing, this one. How many do you get? Don't you get 5? So it will give you n, in other words. Let me try this again. 1, 2, and 3. So you have to skip one of the n's. I don't know which one is experimentally easier. Probably this one is difficult because you will be hitting the piston. So if you count how many maxima and minima, it can tell you n, right? And this is what we did for you. We took a constant frequency. We already have those lengths. Let me show you where the length is. For 1 kilohertz, you had 72, 55, 38, 20, and 30. These were measured by students. We took the same values, okay? And then we counted how many maxima and minima. In other words, we calculated n, okay? We measured actually n, we counted n. And then you see that the length and n are somehow proportional. You will be asked to plot L versus n or n versus L. I can't remember. Obviously, you're going to get a straight line passing to the origin. You have to deduce what the slope represents, eventually find the wavelength, eventually find the speed, and so on. And here I'm explaining again what n represents n is equal to 1 in this case, n is equal to 3 in this case, and this is 5, and this is 7, and this is 9, and this is basically what was happening inside the tube, but you couldn't see it. Okay? So as you can see in this lab report, in this PowerPoint presentation, you have all the results. I did that on purpose because I didn't want you to wait for you to do the lab report and for me to create the results. So I created the results prior. I will save as, and I'm gonna call it 2, because for me you are the second section. All right. Also, I would want to show you the video a bit. However, it's not very visible. The talking is more important because I tried to fast forward. I'm gonna share the link with you definitely. I'm showing you the tube, the function generator, the connections, how I change the amplitude, all right, how I change the frequency. It's very important. Probably you want to look into the smallest subdivision divided by 2 for the uncertainty, how the connections were made, connecting the speaker to the function generator, changing the frequency, and you can hear the sound. This is nice. I did not, you see the amplitude changing as I vary the amplitude knob. But I want you to see what happens when I move the piston. This is the microphone, by the way. It should be at the final end. Probably I'm gonna push it back in a moment. I'm fixing the tube. The piston is, yeah, that's the microphone. You see how tiny it is? You can use it to spy on someone. By the way, those microphones can be ruined so easily. It took us like we tried many to find one that is functioning. I don't know why. Probably, yeah, you see the piston? It's translucent, so it's like white. Okay, so while you watch the experiment, you can, now I'm trying to push the microphone backwards. While you watch the video, think of sources of errors. I did not start taking measurements. This is very low sound. I picked the frequency I want. Now I'm gonna start. Probably I'm playing with the frequency to show you what happens. Okay, I'm gonna start changing the position of the piston. I'm gonna start from this is the piston here. I'm gonna start from very far piston position and then decrease it slowly. Probably you can look at the oscilloscope at the same time to see that at some point the amplitude is increasing, then decreasing. So I will keep on moving the piston forward, backward to find the perfect position that would give me the highest sound on the oscilloscope, or I can simply use my ear. However, my ear has a lot of human error. If I have an oscilloscope, why not look? So here I'm recording the position. I need to find another length that is shorter. Okay, do you hear that? I hope this will not bother you. Okay, then I keep on moving the piston closer and closer to the speaker to find all the positions at which I have resonance. And resonance again means a known number of loops. Okay, so yeah, I know that fast forward will not help you much. You need to watch the video. Okay, let me see if there's anything left. That's it. So yeah, you watch the video. It's gonna be more beneficial for you. And I think that's it. Yeah, I have a feeling that the theory is still a bit difficult for you. I made my best to make it clear, but probably it's still not too clear. So please watch the video and watch the recorded session again and go through the presentation again. Try to read the manual. The manual is important to go through. Probably they have something to make it easy on you. Probably the procedure will help a bit along with the video of the experiment. This is the equation of the sound, speed of sound, and they tell you what to do. Like I did not show you the questions and so on. You see, so basically you just need to plot, find the velocity, and I don't see any error calculation. That's it. Yeah, no error calculation. All right, you people, I'm gonna stop recording and I can